Hello all. In this tutorial we are going to design the core logic of our IP core. So basically we have already designed our line buffers. We have already designed the logic which is sitting after this multiplexers, basically for doing the multiply and accumulate operation. So this time we are going to design the module which is going to instantiate all these line buffers, all these multiplexers, and which controls storing data into line buffers, as well as which controls sending data from this module to the Mac module. Okay, so I'm starting a new file, and let's call it something like image control or something, because we are basically writing the control logic. Okay, so first, again, as usual, we have to write our input output. So we have a clock, we have a reset. Now look at the figure. So we are going to instantiate our line buffers inside this module, and from external world we will have a single stream of pixels coming, and we need to store those pixels into this line buffer, and finally we have to send a stream of pixels from this module to the module for multiply accumulate. Okay, so based on that, this is the input pixels stream. So I need valid also, again like our axis stream interface. This is the input interface. Similarly, we need an output interface, 7 down to 0. Okay, so output interface, if you notice, it is going to the module of multiply accumulate, and if you look at our previous design, the assumption is he is going to get all 9 pixels in parallel. So 72 bits it should be. So it is 71 down to 0 or pixel data, and we have output O pixel data valid. Okay, so that's it about the interface. Now let's go ahead and instantiate our line buffers. So as I mentioned before, for performance improvement, we will be using 4 line buffers. Okay, so not 3. So at one time we will be doing the convolution on 3 of them, and parallelly we will be filling the data in the 4th one. So let's instantiate 4 line buffers. So let's call them like LB0, line buffer 0, line buffer 1, 2, and 3. Okay. So clock we can directly connect, reset also we can directly connect. The data will be this pixel data that actually we can directly connect, and we can manipulate this data valid to control in which line buffer data will get stored. Okay, so directly connect this one. Okay, so this much we can do for all 4 line buffers. 0, 1, 2, 3. Okay, so first thing, let's write the logic which will control which line buffer will get the data coming from the external world. Okay, so this is the logic what I'm going to use. So when we start, first 512 will go here, next 512 here, next 512 here, next 512 here, and next 512 should go back to the first line buffer itself. Okay, so that's how we are going to do it. So we will have a counter which will count how many pixels are received, and whenever that counter crosses 512, we need to fill data in the next line buffer. Okay, so that's the logic we are going to use. Pretty straightforward. So we will have a counter. So let's call it like always at clock. So let's call it maybe some pixel counter or something. I reset. Let's call it pixel counter. It is initially 0. And it will increment whenever a valid pixel comes. Okay, pixel data valid pixel counter +1. So we need to declare it. So I'm going to declare it 9-bit because my aim is to find whether 512 bits of data has arrived. So the logic is whenever the pixel counter overflows, when it changes from 511 to 512, I need to switch to which line buffer the data should go. Okay, so to make our logic simple, we will make it exactly 9-bit so that it can count from 0 to 511. Okay, so pixel counter is this one. Now let's write the logic. Okay, so essentially you are writing a demultiplexer. So you have data stream coming from here, you need to choose where it should go. So I'm going to choose a register which will basically tell me to which line buffer the incoming data should go. So initially, let me call it current write buffer or current write line buffer. So when we apply reset, we are always starting with the first line buffer. Otherwise, what happens is if our pixel counter is 511, that means we already received 511 and we get one more pixel data. Okay, so what happens is on this clock, the pixel counter will overflow to 0 because we declared it only 9 bits, so we can count only from 0 to 511. Okay, so it will automatically go back to 0. So if I write like this basically indicates we already received 511 and this is the 512th pixel coming. Okay, which should be the last pixel going to the current write buffer, and from the next pixel onwards it should be stored in the next line buffer. So based on this, we can say current is, we are just incrementing it. Now this logic will perfectly work if you declare it 2 bits wide. Okay, because if it is 2 bits, it goes from 0 all the way to 3, and we have line buffers 0 to 3, total 4. Okay, so based on this, initially it will be 0. Once we get 512, it will get it will become 1, then next 512 2, then 3, then it will overflow back to 0. So this logic will work. So based on this one, now I can write the valid signal for these line buffers. Okay, so I will have 4 valid signals, so let me write them, 4 of them, 3 down to 0. Let's call it a line buffer data valid. You can write it in a different way. Basically, okay, whichever is the current line buffer, its data valid should be same as this data valid, and all other line buffer data valid should remain 0, so that if any new data comes, it goes to the current write buffer. So one simple way to write it is like that, writing it as combo I'm saying line buffer data valid, all of them 0 except okay. So this is a shortcut. You can write if else if case statement also, no issue, but this makes it shorter. So I'm basically saying like all of them is 0 except the current line buffer data value. Okay, so this will be same as this and everything else remains 0. So based on this, now we can connect them here. 0 1 2 and 3. Okay, so that part is done. So now data will be properly stored in the appropriate line buffer. After every 512 pixels, we are switching to the next line buffer. So that's the write part. Similarly, we can easily write the read part also. Okay, so we'll again have something to indicate from which line buffers we are currently reading, and each time we finish reading one full row, we will switch the line buffers. So basically this multiplexer part. Okay, so that's what we are going to do it. So again, like current write line buffer, we can make something called down to 0 current read line buffer. Okay, now remember our assumption is we are going to get data from 3 line buffers in parallel. Okay, so initially we will get data from these 3 line buffer. Next time we will get data from this one, and the fourth one. Next time this one, and the first one. Okay, so these are the 4 different cases. So let's go ahead and write that logic first, because that is the simplest one. So we'll say like always that again I am writing it as a combination logic. Okay, so let's write it like a case statement. So case and read line buffer end case. The logic for controlling this we will write. Okay, next. But first let's write it. So again, this can have values 0 1 2 and 3. So if we are at 0, we will read from these 3. Next 1, this and this, so on and so forth. So if it is 0, our output pixel, this one, this will be composed of data coming from first 3 line buffer. So okay, so let's declare the data here. This is line buffer 0 data, this is line buffer 1 data, this is 2, and this is 3. Remember, they are all 24 bits. So altogether we concatenate 3 and we will get the 72, which will be ultimately going here for conversion. Okay, so if we are 0, we will concatenate line buffer 0 and line buffer 1 and line buffer 2. Okay, so 4 different cases we can write. So if it is 1, we have 1 here, 2 here, 3 here, and for 2 we'll have 2 here, 3 here, and 0 here. And for case 3 we'll have 3 here, 0 here, 1 here. Next case is again case 0, okay, because we will make our current line buffer. Again, it is only 2 bits, so it may get value 0, 1, 2, 3, and after 3 it will overflow back to 0, so we will again get this case. Okay, so hope it is clear. Okay, so let's go ahead and declare these things quickly. So they are all 24 bits wide, 23 down to 0. Okay, now we will write the logic. Okay, so this should be reg type. Okay, now we need to write the logic which is going to control this current read line buffer. Okay, so similar to current write line buffer, what we need to do is each time we finish reading 512 pixels, we need to switch the current read line buffer. So similar logic. Okay, so we can write maybe here. So always at postage I clock and if that. Okay, initially we will start from 0 itself. Okay, so again, similar to write, we need some counter which counts like how many pixels has been read. We will declare it later. So let me write it now itself. If the read counter is 511, that means you already read 511 pixels and you are again reading data. Okay, let's call it read line buffer. If that is the case, that means you are reading the 12th data, 12th that means you are reading the 512th pixel from the buffer. You have to switch the current read line buffer to 1. Okay, so we need this counter which basically counts how much data you have read. So let's write it again, always at postage I clock. So if reset comes, read counter is 0. If we are reading, we will increment it by 1. Okay, so we will declare all these signals, okay, in one moment. Okay, so first easiest thing to do is now to control this signal, the read signal, because we already have this current read line buffer information. Okay, so similar to our 4-bit line buffer data valid, we can actually declare reg 3 down to 0. Let's call it line buff read data, and we connect them here. So this is for 0, for 1, for 2, this is for 3. So now we need to control these signals. Okay, so again, remember, at a given point in time, you will be always reading from 3 line buffers in parallel, not 1. Okay, in write operation, when you get a new pixel, you have to store it in only 1 line buffer. But while reading, again, go back to the figure, at a given point of time, you will be reading from 3 line buffers together, and you will be sending it out. You may be reading from 0, 1, 2, 1, 2, 3, 2, 3, 0, like that, but you will be always reading from 3 consecutive line buffers. Okay, so keep that in mind. So we already have this current read line buffer, which basically decides from which line buffer you are reading, and based on that you have already concatenated the data, right? So same way, based on this one, you have to send the read enable signal to the line buffers so that it will prefetch the next data to the output, so that when you read next time, you will get it. Fine. So that's what we are writing here. Always that again you have to write it as a combo logic, because we don't have any read latency from this read line buffer. Okay, so as soon as we finish from reading 3 sets of line buffer, we need to immediately switch to the next set of 3 line buffers. So if you write it sequentially, there will be 1 clock latency, and it will mess things up. Okay, so you need to switch as soon as you finish reading from 3. So you need to write it as a combination circuit. Okay, so again let's write it as again this case statement, or you can write if. So same cases. So when the current line buffer is 0, you want to read from 0, 1, 2. So it is already prefetched, so it will go here. So parallelly, you need to send the read enable signal so that he will fetch the next data on the next clock edge. Fine. Okay, so 0 will make line buffer read data of 0. That will get which one? Read line buffer. This is an internal signal. We will declare it. He will get the signal. He will also get this one. He will also get this one, because we are reading from these 3 line buffer, and we won't be reading from this line buffer. Okay, line buffer read data. Okay, should be, we'll declare it. First let's write it. So 0, we write like that, and we are reading from 1. We want to read from this one, and this one, but not from this one. So here we will read from this one and these two. Finally, we have 3. Read from these 3, and this is 1 TB. Okay, now we need to declare them. It's already declared. Only thing is this is capital letter R. So let's okay, 0, 1, 2 is 1 TB 0, and this is 3. When you are copy pasting, be very careful. I am also making mistakes. Okay, read line buffer, we will declare it. Okay, so a few more things we have to declare. For example, read counter, is not declared, so let's declare it like pixel counter. That's also 9-bit. We need to count till 511 and a read line buffer. Okay, let's declare it, and later we'll write the logic how the signal is generated. Okay. Okay. Now we need to generate this signal. Okay, read line buffer. This is the signal which is ultimately controlling from which line buffer you are reading. Okay, so let's come back. How can we do it? So basically, when you start, you can start reading from the line buffers only after filling the first 3 line buffers. Okay, only after filling first 3 line buffers you can start the convolution, and after that you can start reading from them in parallel. And once you finish these 3, if the 4th one is filled, you can read from next 3. Now once you finish that, if the first one is again filled, you can read from this one, 4th one, and the first one, so on and so forth. Okay, so we need to start the read operation, we need at least 512 times 3. Only after getting 1536 pixels, you should start reading from the line buffer. Till that you should wait. Now the easiest way to implement this condition is to write a very small state machine. So that state machine will be controlling when you will start reading from the line buffer, and ultimately this read line buffer signal. Okay, because you need to wait for this much time. And basically you will read from line buffer only if line buffers have at least this much data. In other words, at least 3 line buffers are full, then only you can read from the line buffer. If the data in line buffer is less than this much, you can't read from the line buffers because you don't have enough data for doing the convolution. So again, now we need some counter to check how much data are there in the line buffer. Not only one line buffer, overall how much data is stored in the line buffers. And if that counter is greater than this value, we can start reading. Okay, so for that I need to declare one more signal. So let's call it total pixel counter. Okay, so this counter will basically tell me totally how much valid data are there in the line buffer. So in the worst case, how much we need maximum capacity is like 512 times 4, so 2k. Now to store 2k you will need these many bits. Okay, 12 bits. So let's declare it 11 down to 0 total pixel counter. Now let's write the logic here itself. So okay, so we have different cases. One case is when a new data comes from external world, we can increment this total pixel counter. If we are reading from line buffer, we will have to decrement this total pixel counter because you are already reading from the line buffer, right? And in some cases what happens is on the same clock, data will be coming from the external world as well as you will be reading from the line buffer. So in that case, it's effectively you don't have to change it because you want to increment by 1 as well as decrement by 1, right? So we have to write those cases. So in short, there are only 2 cases where this total pixel counter will change. So first case is you have data coming from external world and this signal is low. You have data but you are not reading from the line buffers. In that case, this will increment by 1. But suppose you don't have data from external world and you are reading. In that case, this will decrement by 1. In all other cases, it should keep its previous value. Okay, so we need this guy for writing our small state machine. Reset. So we'll write a state machine. So let's call the state as read state or something, because this is the state machine which basically controls the read operation from the line buffer. So initially we are in the idle state. Let's begin end case read state end case. So we are at the idle state, and as I mentioned before, we can start reading only after we get sufficient number of data. So that information we will get from this total pixel counter. So if total pixel counter is greater than 512 times 3, that means you have data in at least 3 line buffers, we can actually read. Okay, so total pixel counter, if it is greater than or equal to 1536, you can actually read. So under this condition, we will make this signal high. And what will happen to this signal? Based on whichever is the current read line buffer, that read signal will go to those 3 line buffers in parallel, and data will come out of that. And based on current read line buffer, again data will be selected from 3 line buffers and it will be sent out. And again parallelly, based on this signal, the read counter will be incrementing, and once the read counter overflows, we will change the current read line buffer. Okay, so this although it is a single number like 0, 1, 2, it is actually representing the starting line buffer from where you are reading. You are reading from that line buffer as well as the next 2 line buffers, because you are always reading from 3 line buffers together. Okay, so this should be also initialized to 0 here. And once we find like there is enough data, we will just send one entire row of data. Okay, we will continuously stream data to the output, so that our convolution logic, he gets data consecutively for next 512 cycles. So we'll say like read state is something like okay, read buffer or something, and in this state read buffer, what we are doing is we are just checking whether we are reading 512 pixels or not. Okay, once we start reading from a line buffer, we will read one entire line. And remember, based on this signal, our read counter is already incrementing, so I can check whether I finish reading one entire line or not. Okay, so if read counter, if read counter is 511, okay, that means on this clock I'm seeing 511, read line buffer is already high, that means on this clock I'm going to read the 512th pixel. Okay, read counter will overflow, so you should write 511. Anyway, that is the maximum value read counter can take. So on this clock I am going to read the 512th pixel. If that is the case, okay, we will go back to idle state and we will check whether sufficient data is there in the line buffer. If not, we will wait in the idle state for sufficient data to come. If there is sufficient data, we will immediately come back and read from the next 3-line buffer. And we need to make the signal low here because we finished reading all 5. Okay, so that's it. That's the state machine, very small one, only 2 states. So it needs to be only 1 bit wide and okay, so we declare the 2 states also. Okay, so that's it. This is the entire logic. Maybe you have to go through it once more to really understand what is happening. So basically what we implemented we implemented a demultiplexer here which will choose input stream of pixel and it will decide to which line buffer it should be stored. That is one thing we did. Okay. Another thing that we implemented is this multiplexer. Although you cannot directly see instantiation of multiplexer here, this case statement is actually implementing those multiplexer. And the control signal to the multiplexers are this one, current read line buffer. Okay, so based on which line buffer you are reading, or starting from which line buffer you are reading, you control this multiplexers and take data from 3 line buffers and send it out. Now that control signal is controlled from a state machine. Okay, so that state machine counts. First it checks whether there is sufficient data in the line buffers. If there is sufficient data in the line buffer, it will start reading and it will consecutively read 512 pixels, and once it finishes 512 pixels it will go back to idle state and again wait for sufficient data to come. So the final logic remaining is this signal. How will you say whether pixel data valid signal? Okay, so this signal should be asserted whenever there is a valid data here. When will you have a valid data here? You will have a valid data here whenever your read line buffer becomes high. Okay, again because there is a 0 read latency for the line buffer. As soon as you make it high, there is already valid data at the output of the line buffer. Okay, because it is working based on prefetching. So effectively you will have a valid output whenever the read line buffer becomes high. So if the signal is high, that means the data coming here is valid. Okay, so that completes the design of our this core logic. Again, I am not simulating at this point in time because in next tutorial we will combine all these modules and build our entire IP, and we will simulate then to check whether all our logic is working or not. Thank you. See you in the next tutorial.